Welcome back to the Deep Dive. Today we are plumbing the depths of modern software architecture, looking at a name that, while it might not be instantly recognizable outside of computer science circles, is responsible for the invisible, reliable structure of the digital world you interact with every single day.
That's right.
We are talking about Barbara Liskov.
We are. And if you've ever written a line of code in, say, Java, C++, C#, or, well, really any modern object-oriented language, you're standing directly on the foundation she helped pour.
That's a powerful way to put it.
It's true. She is, quite simply, one of the primary architects of reliable, reusable code. She provided the theoretical rigor that turned programming from a kind of art into a reliable engineering discipline.
So we've taken a stack of sources, chiefly material, detailing her really extensive career, her landmark projects at MIT, and the just staggering array of awards she's accumulated, and we're using that as our map.
Right.
We're here not just to list her achievements, but to understand the profound why behind them.
And that's our mission today. We want to connect the abstract theoretical work she championed. And some of these concepts sound intimidating, like data abstraction or Byzantine fault tolerance.
Yeah, and they do.
And connect them to their concrete practical impact on systems you rely on every day. We want to understand not just what she did, but how her rules ensure that the complex programs running cloud infrastructure, financial systems, and mobile apps don't just, constantly break down.
And when we look at her overall contribution, which spans, 5 decades, it really seems to stand on two massive complementary pillars.
It does.
First, there's the principle of data abstraction, which she formalized through abstract data types and the CLU language. And this fundamentally changed how we organize code at the component level.
And second, there's the Liskov Substitution Principle, or LSP. This is the formal rule she developed for object-oriented programming that defines how different parts of a software system, specifically parent and child objects, must relate to interact reliably.
Which ensures that reusable code truly is reusable.
Exactly. And robust across different implementations.
Right.
You put those two concepts together, and they provide the structural integrity for the entire modern software industry.
Okay, let's unpack this. Starting with the path she took to the highest ranks of computing, which, that itself is a story of intense focus and breaking institutional barriers.
We can start in Los Angeles. Barbara Liskov, born Barbara Jane Huberman, arrived on the scene November 7, 1939. She was the eldest of 4 children.
And like a lot of early computer science pioneers, her story really starts in math.
It does, firmly in the field of mathematics. But the context of her learning environment is absolutely critical to understanding the challenge she overcame.
She got her bachelor's degree in mathematics from the University of California, Berkeley in 1961, with a minor in physics. And the sources highlight a really stunning detail about that time.
What's that?
She had only one other female classmate in her major.
One.
That's not just low representation. It illustrates a deeply, deeply isolated educational landscape for women who were pursuing technical fields back then.
That statistic isn't just an anecdote. It reflects a systemic reality. She was operating in an environment that was, for all intents and purposes, designed to exclude her.
And the challenges weren't just about, being in the classroom. They were actual institutional roadblocks embedded right in the higher education system.
Which brings us to a specific, almost unbelievable historical constraint she ran into when she was applying for grad school right after Berkeley.
The Princeton hurdle.
Exactly, the Princeton hurdle. Liskov applied to top graduate mathematics programs, including Berkeley and Princeton. But the source material reveals a stunning reality. Princeton University was institutionally not accepting female students in its mathematics program at the time she applied.
It was an outright ban.
An outright ban. Think about that for a moment. You have a highly capable, driven, future Turing Award winner, literally barred from a top program simply because of her gender.
It's just astounding. It wasn't about her qualifications.
Not at all. It was a deeply embedded historical exclusion. The sheer intellectual caliber that was being rejected by institutional policy is, it's mind-boggling.
So that forced a pretty significant pivot for her.
It did. And, perhaps ironically, it led her directly into the burgeoning field of computing. Instead of pursuing theoretical math right away, she moved to Boston.
Right.
And she secured her first professional role at the MITRE Corporation, where she worked for about a year. And that exposure to practical systems development was transformative for her.
And after MITRE, she took a programming job at Harvard.
Right.
Focusing on language translation.
Yes, and it was in these professional roles, working directly with machines and code, that her intellectual path really solidified. She recognized that her mathematical mind could be applied with immense power to this new field of computer science.
A field that was, way more open and dynamic than the ossified mathematics departments of the time.
And that strategic pivot was a success. She applied again to graduate programs, and she received her Ph.D. from Stanford University in March 1968.
And this achievement is historically monumental.
Oh, absolutely. She was one of the first women in the entire United States to be awarded a Ph.D. from a computer science department. It's a landmark achievement for her personally, and really for everyone who followed.
And of course, that path led her to become only the second woman, after Frances Allen, to receive the prestigious A.M. Turing Award.
Her doctoral work at Stanford was supported by John McCarthy, one of the founders of artificial intelligence.
Right.
Her thesis was titled, "A Program to Play Chess Endgames." Now, this wasn't about building a full chess engine. That was way too computationally expensive back then.
So it was more focused.
Much more focused. It was about solving incredibly complex, specific scenarios at the very end of a chess game.
And in that thesis, she introduced a really important concept that I think speaks to her focus on efficiency, the killer heuristic. We can't just drop that term without explaining it.
No, we can't.
What did the killer heuristic do, and why was it so vital for early AI?
The killer heuristic is essentially a memory trick. In AI search algorithms, like the ones used for chess, the computer explores millions of possible future moves.
A huge decision tree.
A massive one. And if a move causes a brilliant response that immediately refutes the current line of play, that killer move, the heuristic says you should remember that move and check it early in other branches of the search tree.
Oh, interesting. Even if those other branches seem totally unrelated.
Exactly. It's a way of saying, hey, if this move was really good or really bad over there, it might be good or bad over here too, so test it first.
And that lets you prune the search space, cut off entire branches of that tree early.
Dramatically improves efficiency. It shows that from the very beginning, Liskov's research was focused on creating efficient, clear, and powerful ways for programs to handle complexity. It really set the intellectual stage for her later focus on robust program design and modularity.
That's a fascinating intellectual trajectory. She went from optimizing decisions in a highly abstract game
Right.
to optimizing the fundamental structure of all software. And that intellectual momentum carried her to the Massachusetts Institute of Technology, MIT, where she became an institute professor and a Ford professor of engineering.
The move to MIT defined her professional life. And this is where she turned her focus to the driving problem of the 1970s. The increasing complexity of software.
The inevitable spaghetti code.
The spaghetti code that resulted from that complexity, which was unreliable, difficult to test, and virtually impossible to modify without introducing a whole new set of errors.
It seems like early programming was so procedural. You had variables that were often global, meaning any function anywhere in the system could potentially modify any piece of data at any time.
That's precisely the problem. The core philosophical struggle Liskov tackled was managing that sheer volume of implicit dependencies. As programs got bigger, it became impossible for one programmer or even a large team to hold all the implementation details in their head.
So if one developer changed how they stored a list,
Right, say from array to a linked list.
then another developer's function, one that relied on the old storage method, would just break catastrophically.
The reliance on hidden internal implementation details meant the systems were incredibly brittle. It's like trying to fix a skyscraper by relying on your internal knowledge of which individual steel rivet was used in every single wall.
You couldn't swap out or upgrade components without tearing down the entire structure.
And that need for isolation, for compartmentalization, is what led directly to her pioneering work on abstract data types, or ADTs, and the principle of data abstraction.
Her landmark paper, Programming with Abstract Data Types, from 1974. Foundational stuff.
Truly foundational.
Okay, we need to nail this down for the listener. What is the concept of abstract data types, and how did it impose order on that chaos?
Data abstraction is the idea that a data structure should be defined entirely by the set of operations you can perform on it. Forget about how the data is stored. That's an implementation detail.
So you're only focused on the functional contract.
Exactly. What actions can I perform, and what results do I expect? That's all that should matter to the outside world.
So if I create a stack data type, a standard structure where the last item in is the first item out,
LIFO, yeah.
I define it only by its operations. Push to add an item and pop to remove one. I don't define it by whether the computer stores those items in a contiguous array or a scattered linked list.
Precisely. Liskov's work emphasized encapsulation, hiding the implementation details inside a secure boundary. This makes the code modular, easier to manage, and dramatically more reliable.
Which means if you, the developer, decide to optimize that stack later, maybe you change it from a slow linked list to a faster optimized array.
The rest of the program that uses your stack doesn't need to change at all, not one line of code.
Because the abstraction shields the rest of the system from the change. That's the core insight that enables continuous improvement and rapid iteration today.
Absolutely. You can swap out an entire microservice without telling the front end, as long as that service maintains its external contract, its API.
It's the same principle.
It's the exact same principle. And Liskov didn't stop at theory. She created a language to enforce these principles rigorously. This was the CLU project, developed in the 1970s.
So CLU was designed explicitly to embody these ADTs. What was the specific language mechanism within CLU that enforced this abstraction?
CLU introduced the concept of the cluster. A cluster was the fundamental structure for defining an abstract data type. It grouped together the data structure itself and the set of procedures or operations that acted upon that data.
Okay.
And crucially, CLU strictly enforced that the data within the cluster could only be manipulated by the procedures inside that same cluster.
That sounds like the direct conceptual ancestor of the modern class structure,
Sure.
where you have private internal fields and public methods.
It is the direct ancestor. The cluster concept, this idea of a data type that owns its state and exposes only a defined set of operations, was revolutionary. It provided a powerful, disciplined tool for structuring large software systems.
And this brings us to the key aha moment for anyone interested in programming history. While CLU itself might not be used today,
No, it's not.
its DNA is everywhere.
That is the core legacy impact. The mechanisms CLU introduced for data abstraction clusters, its methods for exception handling, iterators, were enormously influential on the design of several later, massively popular programming languages.
And the source material specifically calls out some big ones.
The biggest, it references Java, C++ and Data, C#, and Ada. When you use classes, when you define interfaces, when you enforce data hiding using private or protected keywords in any of these modern languages, you are applying concepts traced directly back to Barbara Liskov's work on CLU.
So to sum up this part, she basically defined how modern languages organize data for reliability and reuse. She provided the blueprints for building modular software components that don't leak their fragile internal details.
Well said.
So data abstraction fixed the component level, how we define a single, robust data type. But the field kept evolving, right? And soon, object-oriented programming, OOP, introduced these complex relationships between types.
That's right.
So the next challenge was figuring out how to manage inheritance and subtyping as programs grew.
Abstraction fixed the internal structural integrity of a component, but OOP introduced a new mechanism that threatened to undermine that integrity: inheritance. You had a base type, let's call it T, and a new subtype, S, that inherits from it.
Okay.
And programmers wanted to be able to substitute an object of type S anywhere an object of type T was expected.
So if I have a base class called animal and I create a subclass called dog, I should be able to pass a dog to any function that expects an animal without, worrying about crashing the system.
Exactly. The problem was traditional type checking only looked at the structure. Do the methods have the same names and the same number of arguments? But what you really need is a rule that ensures behavioral compatibility.
What do you mean by behavioral compatibility?
Well, if the dog suddenly violates an implicit guarantee made by animal, say, the animal.eat method always consumes food, but the dog.eat method sometimes just throws the food away, then substituting the dog breaks the system's expected behavior.
Even if the method name is the same.
Even if the structure is identical, the behavior is wrong. And this need for a formal mathematical rule to govern how these subtypes should relate to their base types to ensure the overall code remains robust led to the development of what is known universally today as the Liskov Substitution Principle, or LSP.
She developed this principle with Jeannette Wing.
She did, and it was formally referenced in their 1994 paper, A Behavioral Notion of Subtyping. And that phrasing is key. It is specifically a behavioral notion of subtyping. It focuses not on structural similarity, but on how the subtype acts in the system.
Okay, so let's tackle the dense definition first, and then we'll immediately make it accessible. What's the formal statement of the LSP?
The LSP states, if S is a subtype of T, then objects of type T may be replaced with objects of type S without altering any of the desirable properties of the program.
Okay, that is classic computer science formality. It's concise, but a bit abstract. The implication, though, is incredibly powerful. And I think the best way to clarify why structural inheritance isn't enough is with that classic analogy, the square and the rectangle.
The perfect example. Structurally, a square is a type of rectangle. A rectangle has a width and a height, and you have procedures to set those independently.
Right.
A square has a side length, but mathematically you could say it's a rectangle where width equals height.
So if we follow the basic structural inheritance rule, it seems logical to make the square class inherit from the rectangle class.
It does seem logical. But here's the behavioral conflict. The rectangle class guarantees that you can set the width to 10 and the height to 5. That's part of its contract.
Okay.
Now, if I substitute a square object where a rectangle object is expected, and the program calls setWidth and then setHeight 5, the square object must break that expectation to maintain its own invariant, which is that width must equal height.
So it might force the height to 10 as well, or maybe throw an error.
Right. It does something unexpected. The square subtype violates the behavioral contract of the rectangle base type, which implicitly promises that setWidth does not affect height. Any code expecting a rectangle will now get an unexpected outcome when dealing with a square.
And that's a violation of LSP? That's where bugs come from.
Exactly. The square rectangle problem shows that subtyping must be based on observable behavior in contracts, not just structural convenience. The LSP ensures that the subtype upholds all the implicit and explicit guarantees, the preconditions and postconditions of the base type.
Here's where it gets really interesting for software architects. This principle ensures true reliability and reusability. Because if a code base strictly adheres to LSP, I can write general code that works with the base type, and I know that any new specialized subtype that someone adds 5 years from now will work perfectly with my old code.
It creates a system that's robust against future specialization. It forces programmers to think about the contracts their code makes, rather than just the structure.
It seems like it connects directly to modern concepts like interface segregation and solid design principles.
It's the L in solid. It promotes decoupled, maintainable code bases. Without LSP, object-oriented programming would be a fragile mess of unpredictable substitutions.
And the power of this principle is still recognized today, nearly 30 years after that paper. The 2023 citation she received for the Benjamin Franklin Medal specifically recognized her work for, what was it? Enabling the implementation of reliable, reusable programs.
That citation is a testament to the fact that her work didn't just solve an academic problem. It gave the software industry the necessary guardrails to scale complexity. It's the invisible structural integrity that makes large systems manageable, testable, and reliable.
That's a fascinating evolution, from fixing data encapsulation on a single machine with CLU to defining structural rules for inheritance with LSP. But her career didn't stop at the boundaries of a single program.
Not at all.
Her focus naturally evolved to the ultimate complexity, handling multiple machines working together, often across vast distances.
Her career trajectory shows this consistent march towards solving the biggest problems in system integrity. She started with making programs reliable, and then she moved to making entire systems composed of multiple, often distant, machines reliable, even in the face of failure.
This is the domain of distributed computing and fault tolerance.
Right. And we see evidence of her early leadership in system design right after she joined MIT, where she led Project Venus.
What was Project Venus?
The Venus operating system was an important early leadership role for her. It was developed as a small, low-cost time-sharing system, focusing on efficient resource management, a very practical system architecture challenge. But the next stage, Argus, was her seminal contribution to distributed programming.
Detail Argus for us. When was it developed, and what was its core innovation?
Argus was developed in the 1980s. Its historical significance is massive. It was the first high-level language specifically designed to support the implementation of distributed programs. It introduced these concepts of guardians and atomic actions.
Guardians and atomic actions. That sounds like she was trying to package up that CLU abstraction idea and scale it across a network.
That's a great way to put it. A guardian was essentially a container for data and processes that could persist and be located across the network. And atomic actions were Argus's mechanism for managing distributed transactions.
Which ensures that operations across multiple machines are all or nothing.
All or nothing. Either every machine commits the change successfully, or if any one machine fails, they all revert back to the previous stable state. This is the foundation of reliable networked operations, like booking a flight and paying for it.
And Argus also demonstrated a specific technical achievement that is crucial for performance optimization in high-latency network environments. Promise pipelining. That sounds complex, but essential for speed.
It is. Promise pipelining is a technique to hide latency. When a request is sent across a network, say from machine A to machine B, instead of just sitting there and waiting for B to respond before sending the next related request.
Which is a huge waste of time.
Can send several requests sequentially, assuming the prior ones will succeed. It's sending a promise of the next step.
So instead of request 1, request 2, you send request 1, then immediately send request 2, and then you can wait for both replies in sequence.
Yes. You essentially pipeline the communication, significantly reducing the perceived latency in a system where communication delays are the primary bottleneck. Argus really laid the groundwork for managing distributed transactions and communication efficiently.
This expansion into distributed systems eventually led to her most critical contribution to system architecture in the modern era, and it's one that is absolutely essential for things like blockchain, financial ledgers, and secure cloud infrastructure.
You're talking about her research focus on Byzantine fault tolerance.
Yes,
To put this in context, reliability in the 1970s meant protecting against simple software bugs. Abstraction solved that. Reliability in the 80s meant protecting against simple crashes. Distributed transactions solved that.
And reliability in the 90s.
Reliability in the 1990s meant protecting against malicious, unpredictable failures.
That is the crucial distinction. We've moved beyond fail-stop failures, where a component just stops working and is easily detected, to arbitrary or Byzantine failures.
An arbitrary or Byzantine failure means a component might send one piece of information to one part of the system and a contradictory, false piece of information to another part. It's actively lying or acting erratically.
The core challenge becomes, how do the remaining honest components reach a consensus when they can't trust the messages they're receiving?
That's the challenge, is the famous Byzantine general's problem. Commanders trying to agree on whether to attack or retreat, even though some messengers, or even some of the commanders themselves, might be traitors actively trying to sow confusion.
And this is where Liskov, working with Miguel Castro, made a pivotal practical breakthrough in the 1990s. Their 1999 paper, Practical Byzantine Fault Tolerance, or PBFT.
That paper demonstrated how a system could tolerate these kinds of failures efficiently.
What was the key insight that made their solution practical? Because previous BFT solutions were often just too computationally expensive to use in real-world systems.
The PBFT approach focused on optimizing the communication requirements. Previous solutions required every node to communicate with every other node, which leads to this massive exponential overhead.
Right.
PBFT significantly reduced the number of messages needed to achieve consensus and commit an operation, provided a certain majority of the nodes were honest.
Which means they created an algorithm that allowed an honest, functioning system to isolate the malicious nodes and continue operating, confirming the state of the system quickly and securely.
Absolutely. This work is vital for trust. If you rely on a shared ledger or a large cloud system, you need guarantees that a single compromised component can't arbitrarily corrupt the entire database or provide contradictory results.
And PBFT provided a fundamental, proven mechanism for creating digital trust in untrustworthy environments.
And that area-distributed computing and fault tolerance remains her current research focus at MIT.
That is a staggering arc of research. From making an efficient chess algorithm in 1968, to defining the structure of classes in the 70s, to establishing the rules for inheritance in the 90s, and then solving the consensus problem for global systems at the turn of the millennium. It's a career consistently focused on translating theoretical rigor into practical robustness.
Incredible.
Solving these deep structural problems naturally led to, well, significant recognition across the field. When you look at her list of honors, it immediately establishes her status as a true pioneer whose work touches every corner of computer science.
Her career culminates in this extraordinary collection of awards, demonstrating recognition across programming languages, methodology, systems design, you name it. And as we noted early on, we have to pause to reiterate the significance of the historical barriers she broke.
She is the second woman ever to receive the A.M. Turing Award, often called the Nobel Prize of Computing. Considering the hurdles we talked about in her early career, that achievement is just all the more profound.
Let's maybe detail the major awards, because the citations themselves really summarize the immense scope of her influence. We can start with the I.E. John von Neumann Medal, which came first.
That was in 2004.
2004. And the citation specifically recognized her for fundamental contributions to programming languages, programming methodology, and distributed systems.
That's the perfect summary. It hits her work on CLU, LSP, and Argus BFT all at once.
It does. Then, of course, the big one, the A.M. Turing Award for 2008.
She received it from the Association for Computing Machinery, presented in March of 2009.
And the award was explicitly given for her fundamental work on programming language and system design. The ACM cited her contributions to the practical and theoretical foundations of programming language and system design, especially related to data abstraction, fault tolerance, and distributed computing.
It's just so rare to see a career that bridges the theoretical language design work, how a single programmer writes code, with the massive practical systemic challenges of distributed fault tolerance. The Turing Award recognizes the totality of that.
And the awards just kept coming into the next decade. In 2012, she was inducted into the National Inventors Hall of Fame.
Recognizing the invention of her principles and languages.
Exactly. And as we mentioned in the context of the LSP, she received the Benjamin Franklin Medal in 2023 for enabling the implementation of reliable, reusable programs.
And beyond these major technical awards, she's been recognized broadly by the academic community, receiving multiple honorary doctorates.
From ETH Zurich, the University of Lugano, the Universidad Politécnica de Madrid.
She's a fellow of all the major academic bodies, the ACM, the American Academy of Arts and Sciences, and a member of both the National Academy of Engineering and the National Academy of Sciences.
And to emphasize her standing within MIT, she holds the title of Institute Professor, which is reserved for a very, very small number of distinguished faculty. She was also recognized back in 2002 as one of the 50 most important women in science by Discover magazine.
It's so clear that the impact she had on the design of software structure is generational. And before we wrap up, it's also nice to briefly note a personal legacy that has followed in her footsteps.
It is. Barbara Liskov married Nathan Liskov in 1970. They have one son, Moses, who also pursued computer science.
He also earned a Ph.D. from MIT, right, in 2004.
He did. And now he teaches the subject at the College of William and Mary. It's a multi-generational commitment to advancing the core tenets of the field.
So, to synthesize this immense impact, her entire career demonstrates this consistent, decades-long focus on elevating software engineering from, a highly customized, fragile craft into a disciplined, scalable engineering practice.
She invented the rules that govern good software structure. She ensured systems could grow without collapsing.
Her theoretical concepts, the requirement of abstraction through ADTs, the necessity of behavioral subtyping through LSP, and the ability to maintain consensus through BFT, they're not just academic footnotes.
No, not at all. They are the core intellectual property underpinning the robustness of critical modern digital infrastructure. Without her insights, complex code bases would collapse under their own weight the first time an engineer needed to swap a component or update a data structure.
Stepping back, her work really defined the rules of structural integrity for object-oriented systems and distributed networks.
It did. She ensured that when you try to build something bigger than a simple script, the theoretical foundations are sound enough to prevent catastrophic failure, even when parts are being swapped out, or, critically, when those parts might be acting maliciously.
It's a powerful reminder that the complexity of the digital world is managed not through brute force computing, but through elegant fundamental principles. And Liskov provided the conceptual clarity needed to handle massive collaborative software projects reliably. So we end with this provocative thought for you, the listener. Remember that Barbara Liskov's doctoral thesis, the work that launched her career in computing, involved designing a program to solve complex niche problems and chess endgames. It introduced the killer heuristic.
Highly specific and academic.
Very. Yet that kind of fundamental theoretical work, whether it's optimizing search in a game, defining theoretical abstraction, or solving the Byzantine generals problem, so often becomes the invisible, critical foundation for trillion-dollar industries.
That's a great point.
Her early work laid the groundwork for robust class structures in Java and C++A, and her later work underpins consensus mechanisms used in blockchain and high-security cloud networks. So the question is, what other seemingly esoteric research in computing, mathematics, or pure science today?
Maybe in quantum computing algorithms or new mathematical concepts for trustless systems.
Exactly. What research like that will define the next generation of our digital world? Something to mull over as you encounter your next line of code or interact with your next piece of robust digital infrastructure.